Okay, so now we're going to get into robot stuff. So the first objective that we need to have is, given where we want the robot to move and how we want it to move, we need to know how the wheels are supposed to move in order to make the robot do that. So I guess the first question is where we want the robot to go. And with an omni-robot, because you have so much freedom of movement, you need a way to define specifically where the robot's moving to. And so the way a robot can move is, first of all, it can move laterally in any direction. And so that can be specified by a vector quantity. It's moving this fast in this direction. But the robots can also do rotations. And that can be specified by just a simple number. The robot is rotating this much to the right, let's say, and to make it negative, it would be so much to the left. And so any combination of a vector velocity and a number rotation can describe any movement that you want the robot to do. If you want to try and figure out how to get these numbers, some common ways are you can use one joystick for finding the x and y coordinates of your lateral velocity, and you can use the other joystick, just the x-axis for turning, so you could push it like one joystick like this to make the robot go forward, and then if you wanted to turn, that would be the second joystick. Another way you can do it is, if you wanted your first joystick to make it behave like a tank robot, you could do forward, backward, and rotation on that, and then use the second joystick to get your sideways velocity. There's really a lot of ways you can do this. I'm sure you could incorporate a steering wheel or something ridiculous if you wanted to, but these are the two most common ways, I guess. Okay. So, now, once you find where you want the robot to go, you have vector velocity and your rotational value, you need to find out where the wheels are going to go. So the first step to that is you need to know where the wheels are on the robot. And that's going to be defined by your robot design, how your wheels are spaced out on the actual physical robot. And so we know what that is, we can define it, and I'm going to call it current position. And then we calculate where the wheels are going next. And so that's, in my terminology, the next position. And in order to find the wheel velocity, we simply subtract those two vectors. Okay? So I'm going to do this for translation and rotation separately because it makes it a little easier. So, as an example, this would be a common setup for a robot to have 4 wheels in the corner. You don't necessarily have to. Some people do omni-drive with only 3 wheels on their robot, or there's other configurations. This is a common one, so I'm going to use it. And we need to define where these wheels are on the robot. And so we go out and measure the wheelbase and come up with some values for the vectors. That might look like this. One of the important things to notice is that although the ends of the vectors have to be defined by where the wheels are on your robot, you can make the start of them anywhere you want. It doesn't necessarily need to be the geometric center of your robot. And the cool thing is, at the end, the starting point is going to be your center of rotation. So, for instance, in a game like this here, a lot of teams using the omni-drives wanted to be able to spin around the ball. And so, you might want to make your center of rotation here so that you'll be able to hold up the ball easily while turning. But for just because it's easier and it looks a little more intuitive to use the geometric center of the robot, and in most games that's what you're going to want to do. So I'm going to use this as a starting point for this. Okay. So now we need to calculate where the wheels are going next. So here is our velocity vector. That's where we want the robot to drive to. And if the robot were to move to this position without rotating, then all the wheels would need to move by the same amount as a whole overall robot. In other words, all these green vectors need to be the same, because if there are any different sizes or angles, the robot at the end would have rotated a little bit. So in other words, if you want your robot to move without rotating, you need to move each of the wheels by the same amount as the overall robot. And then our next wheel positions, which we need to find, will be represented by blue vectors. And so what we've done here is if I were to use this wheel in particular, taking the wheel position and the robot velocity and add them together. And that's how we get our next position. So mathematically, we express it with an equation like this. Now, I'm going to take, in order to find the wheel velocity, we need to subtract the current wheel position from the next position. And so when we sub in this for the next, what we find is that the wheel velocity is quite simply equal to the robot velocity. And that kind of makes sense. If you think about, an example is if you have what's called a swerve drive robot where all your wheels can rotate around, if you want your robot to go in this direction, say, you simply point all your wheels in that direction and make them drive the same speed. So it makes intuitive sense. Okay, so rotation is quite a bit more complicated. Defining where the wheels are is exactly the same as for translation. It doesn't change. But in order to calculate the next velocity, what we want to do is we want the robot to rotate around. And the consequence of that is we want all the wheels to rotate around a little bit. And what we might notice is that if we were to express these vectors in polar coordinates, what we're doing is keeping the magnitude constant, but simply adding on a certain amount to the angle. And yeah. And so all these angles are going to write the same angle onto each of those vectors. And then our velocities are simply the next vector we find minus our original one. So it gets a little ugly because we have to use trigonometry to convert from polar coordinates back to Cartesian coordinates. But basically, if you think this will be the magnitude of your original position vector, and then this is the angle of the original position vector. So what we want to do is add a certain amount onto that vector. The question is how much. And we certainly want to add on a value proportional to our original input for how much the robot should rotate. That makes sense. But the trouble is most of the inputs that you use, joysticks for example, will be between -1 and 1. And making it go -1 radians or degrees, it doesn't really make sense because it's not necessarily the right value that we want. So we need to multiply it by scaling constant. And then if we were to subtract concurrent, it looks like this, just some values. The problem with this is, and it's not too big of a problem, it's only a slight problem. We did a swerve drive last year, and we used that method for finding rotation values. So we can do it, but the slight problem with it is, let's say I make k equal to 180 degrees, or 5 radians. The problem with that would be that the next wheel position would be at the complete opposite corner of the robot from the original position. And so the velocity would look something like that when we subtract the vectors. The issue is, if we want to do this to all 4 wheels, you find that they're all trying to go towards the center of the robot. And obviously that's not going to go anywhere. So, the problem with this is that the equation we found on the last slide, they only work for very small values of the scaling constant. And so you don't want to move the wheel by too much. But there is another way that we can do this that's a little better. If we take just one wheel as an example, and so if small values of this change in angle are better, then ideally the best value would be when this angle is 0. Now obviously you can't practically do that because then the length of our velocity vector would be 0. But hypothetically, what you might notice is as that angle gets smaller and smaller, this velocity vector becomes exactly perpendicular to these two vectors. And so, if we were to find a perfect velocity vector, it would be exactly 90 degrees away from our position vector. And so that's really useful because we can now specify the angle of this vector exactly, because we know the angle of the original position vector, we can find it. And so the angle of this new vector is simply that angle plus 90 degrees. Geometry. And so the question is, what should the magnitude be? And the answer is, it needs to be how much we want the robot to turn, multiplied by the length r. And the logic behind multiplying it by r is if we had a wheel that was twice as far out as our original one, the circle that it would make around the robot in its path would have twice the circumference, and so it would have to go twice as fast to make it around that circle in the same time. So we need to multiply that out. And so the result is our x velocity is going to be magnitude that I just explained. And this is just converting from polar coordinates. And the angle is going to be the original angle of the position vector plus pi by 2 is just 90 degrees represented in radians. So 90 degrees, pi by 2, same thing. Now the neat thing here is you can use a bit of advanced trigonometry called the double angle formula. If you don't know what that is, it's just because trig functions are kind of weird. And so we can simplify this down to these sets of equations. And so what you might notice with this is that r sine theta, if you look at your equation for polar coordinates, is simply the x value of our position vector, or y value of the position vector. And our cos theta is simply the x value. And so, at the end of the day, our rotation numbers work out to very nice linear equations. And so, to combine rotation and translation together, it's quite simple. You add the vectors together. And so, if you remember, in order to do that, we add the x and y components. And so, if you wanted to do it the first way, the complicated way, that's what it would look like, just summing the values from previous equations. And second way, it looks much neater, and it's a much more elegant solution. The equation would look like that. Okay. So just as an example, for each wheel, you have to take these sets of equations and find the velocity at that wheel. So if we have a four-wheeled robot, we need to do that 4 times. And so this is just an example. If we wanted the robot to go up and to the right and turn to the left, our wheel velocities might look something like this. And so just to put this in perspective, these green vectors represent where the wheels are actually going to move physically on the robot. And so the idea is if we can figure out where they're supposed to move, all we have to do is then find some way to move there, and our robot will do what we expect. So, yeah, let's just first summarize. We know where the wheels need to go, and now we need to determine how we get them there. And that's what I'm going to talk about with the more specific part of the presentation with different kinds of wheels. Before that, are there any questions?